Oh, hi there. I was just doing some bird watching. Here's a fun example I want to take a look at. It involves stickers and arrays. There are 8 rows of 3 bird stickers in Dawn's sticker album. There are 6 rows of 3 stickers in Lindsay's album. How many bird stickers do they have in awe? Well, again, let's use an array to help us with this puzzle. We want to know how many stickers Dawn and Lindsay have in awe, but before we answer that question, well, we need to know 2 things. How many bird stickers does Dawn have in his album? And how many bird stickers does Lindsay have in her sticker album? Well, we know Dawn has 8 rows, and in each row he has 3 bird stickers. And if we multiply to find how many stickers he has, we'd have to do the 8 number of rows times the 3 bird stickers in each row. That gives us 24 bird stickers. So Dawn has 24 bird stickers in his album. Now let's take a look at Lindsay's sticker album. Well, she has 6 rows of bird stickers, and in each row she has 3 stickers. Let's go ahead and multiply to find her number of stickers. 6 rows times 3 stickers in each row, well, that gives us 18 stickers. Now remember, the question was asking us to find the number of stickers they have in awe. Well, what does in awe mean? That's just the sum. So if we take Dawn's bird stickers plus Lindsay's bird stickers, that gives us the bird stickers in awe, and we already have that information. Dawn has 24 bird stickers that we just found with our array, and Lindsay has 18 bird stickers. That equals 42 bird stickers. And there you have it. Arrays are powerful tools that help us organize information and find answers. And I'll see you next time with some more fun examples.
Okay, so let's do some practice today with the commutative property of multiplication. Okay, so the commutative property of multiplication basically states that when you change the order of the factors, the numbers that you're multiplying, the product or your answer is going to stay the same. Okay, so as long as I have the same 2 factors, my product is always going to be the same, regardless of which order I add them in, okay? So to go through some examples to make it make sense, I'm gonna do a couple examples with you, okay? Okay, so let's look at our first example. It says that Dave works at the bird store. He arranges 15 boxes of birdseed in rows on the shelf. What are 2 ways he can arrange the boxes in equal rows? Okay, so let's think about that. I know I need to have a total of 15 boxes, okay? No more, no less, exactly 15 boxes, okay? So no matter what numbers I multiply together, I need to know that, or I know that this factor multiplied by this factor has to equal 15. Okay, it's got to equal 15 no matter what. Okay, so I'm going to look at my multiplication chart, and I might also think about what numbers can I multiply together to get 15. Okay, so I know one way. Let me draw that for you. Okay, so here's my picture of 15 boxes of birdseed in rows on a shelf. Okay, so let's start by looking and thinking about the picture. How many rows are there? 1, 2, 3, 4, 5. I have 5 rows. Okay. How many tiles are in each row? In each row, I have 1, 2, 3 tiles. So I have 5 rows and 3 tiles. I'm going to multiply those two. And all together, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So altogether, I have 15 tiles. Okay? So in this equation, my factors are the numbers 5 and 3. They're the two numbers I'm multiplying together. And my product is 15. That's one way I can arrange 15 boxes in an array to show how many. Okay? Now, suppose my friend Dave doesn't do 5 rows. He instead does 3 rows. What would his picture look like? Would it look different? Let's find out. So instead of 5 rows, we're going to do 3 rows, and we're going to make sure we have the rows equal and have 15 all together, okay? So let's go ahead and let's make that picture. Remember, 3 rows and 5 in each row. Let's see what that's going to look like. Okay, so have a look at our drawing of 3 rows and 5 in each row. Does this array look the same as the array we did initially? No, okay. Does it still have 15 in it? Yes, but we arranged them differently. Let's see what our two factors are, okay? So if we look at the number of rows, we have 1, 2, 3 rows. So our first factor in this case is going to be a 3. And I have in each row 1, 2, 3, 4, 5. So my next factor is going to be a 5. I'm going to multiply them together, and it equals 15. So let's look at the factors we use. In this case, we had a 3 and a 5, and then the answer was 15. What I noticed about these is when we're using an array to help solve a multiplication problem, okay, the answer stayed the same if I had the same number of boxes. The only thing that changed were my factors, and they didn't even really change. The order changed. I have a 5 and I have a 5. I have a 3 and I have a 3. Okay, so 5 times 3 equals 15. But 3 times 5 also equals 15 because my factors are the numbers that I'm multiplying stays the same. Okay, so 5 rows of 3 is 15 and 3 rows of 5 also equals 15. Okay, it's kind of like just turning the array a different way to represent the problem. Okay, why don't we try another one together? Let's look at our next example of the commutative property of multiplication. Remember that the commutative property of multiplication states that when you change the order of the factors, the product stays the same. Okay, so look at the two pictures here. Okay, I have 2 different pictures. Let me draw a line so you can see that. Okay, so in the first one, here on the left of your screen with the brown dots, okay, I have 1, 2 groups, okay? So that's where my factor of 2 comes from. My other factor is how many are in each group. So if I look at the first group, okay, I have 1, 2, 3 counters or 3 circles, okay? My next group also has 1, 2, 3 circles or 3 dots, okay? So that's telling me that my factor that's missing is a 3. So I have 2 groups of 3, and all together, I have 1, 2, 3, 4, 5, 6. This picture shows me that 2 groups and 3 in each group equals 6 altogether. Okay? Now, if I look at my next example on your other side of your screen, we have the same idea, but the picture looks different, doesn't it? So let's see. I have 1, 2, 3 groups this time. There's my factor of 3. My missing factor is how many counters are in each group. So let's count the first group. How many counters are inside the group? 1, 2. There's 2 counters in this group. Let's see how many are in the next group. 1, 2. How many are in this group? 2. 1, 2. How many are in this group? 2. So my missing factor is going to be a 2. And then I accidentally wrote the answer in there, but we're going to find how many altogether by counting the dots in the group. Altogether, 1, 2, 3, 4, 5, and 6. So altogether, there are 6 counters. Now, if we look here, and I think about these 2 equations, okay? Now, the groups are equal, okay, in both instances, but the equations look slightly different, don't they? But if I think about it, if 2 times 3 equals 6, right? Correct? I can kind of think about that as being equal to 3 times 2. They're the same because 2 times 3 equals 6. 3 times 2 equals 6 also. The only difference is your factors have switched orders. Instead of saying 2 groups of 3 or 2 times 3, we're saying 3 groups of 2 or 3 times 2 equals 6. Okay? The numbers and the groups and the number of groups just switched order. Okay? But in the end, the factors are still the same. So your product is going to be the same. Right? Let's do one more example. Then I'm going to have you try a few on your own. Okay, so let's look at this example of the commutative property of multiplication. So first thing let's do is let's look and see if we can write a multiplication equation that matches this picture. Okay, so let's count the number of groups first. Ready? 1, 2, 3. So I know there are 3 groups times, let's see how many are in each group. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. There are 3 groups of 4. And let's count and see what is 3 times 4. How many counters in all? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So altogether, there are 12 counters altogether. Now, let's take and create our own problem, all right? Using the same factors as 3 and 4, okay? But I'm going to reverse them. So instead of 3 times 4, I'm going to draw a picture for the problem of 4 times 3, and it's also going to equal 12. Hopefully, we can double check that in the end, okay? So let's start with our first factor of 4. 4 tells me I'm going to have 4 groups. 1, 2, 3, 4. Okay, I have 4 groups. My second factor of 3 tells me I'm putting 3 counters in each group. Help me count the 3 counters in each group. Ready? 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, so are there 3 counters in each group? Yes. Now, let's see how many we have all together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I still have my product of 12. I still have the same factors, right? I have a 3 and a 4. So I'm going to get the same answer as 12 because 3 times 4 is equal to 4 times 3 because 3 times 4 equals 12 and 4 times 3 equals 12. My factors are the same. They're just in a different order. So I'm going to get the same answer. Okay, so now I'm going to give you some problems. And let's start by just writing multiplication equations for the pictures that you see. Okay,